How's it going, AS Math? It's Mr. Nightback, and we are going to continue our trig unit. We are actually going to look at these things called sectors and what an arc length is and how we can solve problems with those things. When I think of a sector really just reminds me of like I like to think about pizza or pie. I don't know if I'm just a hungry person normally. But that's basically what we're dealing with. We have like this pizza slice that's coming out of this larger pizza. But really we call these, instead of slices, we can call them sectors. Sector is just the shape enclosed by an arc. So an arc would be kind of a part of the circumference of the circle, and then the two radii. So either sector that you're looking at, you're still going to have some kind of radius that's coming out of it, whether that be this radius or the radius left over, and then you're going to have some kind of arc. The major sector is the bigger arc, and then we have this minor sector that has this smaller arc. And so really a minor and a major sector, the only difference is the minor sector is just smaller than a half circle, whereas the major sector is larger than a half circle. That's really the only two differences between them. And again, I like to think about it as just like pizza. So instead of saying pizza slices for now on, or like a slice of pie, you're going to say, I would like a sector of pizza, please. And then you will be the coolest person and least obnoxious person at all the dinner gatherings. Of course you will. So let's break this down a little bit more and think of what we could come up with in terms of measurements. So an arc length, like I said, an arc length is really just a part of a circumference. So really what this boils down to is you have some kind of radius that's enclosing your arc, you have some kind of angle, and so basically if you want your arc length, all you got to do is multiply your radius times that angle measurement, and that'll end up giving you this arc length in purple on the outside right here of this circle. One thing to note, the angle, it must be in radians. So be sure to convert if you need to, or maybe it'll already be in radians and you can just throw it into this equation. Okay, very important it's in radians. Now if we look at the area of a sector, so now we're actually getting like this enclosed green area right here. Well, the area of a sector is really just like part of the area of a circle. And so if we think of the area of a circle, we have pi r squared. But if I want a fraction of that circle, well, what I do is I take whatever angle I have in radians and I'm going to divide that by 2 pi radians, so the angle it takes to go all the way around the circle. And so no matter what, there's no way you're going to get a sector that is ever larger than 2 pi. It wouldn't even be a sector at that point, it'd be a circle. So even if we had something, a sector, that went all the way around, 2 pi over 2 pi would just go to 1, and we'd be left with the area of a circle anyway. So just depending on whatever your angle is, that's how it's going to determine what your area of your circle is. And actually, if you notice, with this fraction, I can actually cross off a pi, which is nice. And so I end up getting, for my area equation, I just get 1/2 r squared times theta. And that's it. That's what it boils down to. So with this arc length equation and this area equation, and of course we're going to be using the law of sines and cosines and that triangular area equation. With all of those, we are going to start solving these problems. Now, these problems they're tough because there's a lot of moving parts with them. And so, again, these are kind of like, even when they're not Cambridge problems, they feel like Cambridge problems. So, be patient with yourself, for one. And secondly, we're just going to have to see some examples and get like wide examples that kind of encompass all these ideas together, okay? So I've done 2 of them for you for the sake of time. So example 1. All right, it's technically a 3-parter, disguised as a 2-parter, A and B. So the figure here, it's a sector of a circle. You can kind of tell, it looks like a pizza slice, right? but it's broken up into a triangle, like a or not a right triangle, but it's broken up into a triangular part right here, and then kind of like this little shaded area. But all together, this entire figure is a sector. It's got a circle O, radius 6 centimeters, and then our angle is 2 pi over 3. For part A, part 1, part A, which just pains me to say, it says calculate the arc length, the perimeter, and the area of the sector. So we need the arc length here from A to B, the perimeter, so from A to B and then some, and then the area of the entire sector, okay? Part B is then going to want us to actually find the area of the purple region, and then part 2, we'll get back to it. We want the exact length of chord AB. We just want to find that. So we got a lot of things we got to find. Let's start from the top, okay? So if I'm doing part 1, part A, it wants me to find the arc length first. Well, I'm just going to use my arc length equation. I know it's radius times theta. And so my radius is 6 centimeters. My theta is 2 pi over 3. I throw it all in an equation, and I just get 4 pi centimeters. If you would like, you can multiply the 4 times pi. That's also, of course, okay, because that's what you're doing. But I like to leave it as pi, just so we get a more exact answer, just because pi never ends, right? It keeps going. If we look at the perimeter now, right, so we now have this arc length, that's part of our perimeter. So I'm going to take that 4 pi, and then I'm just going to add 6 plus 6, so 2 times 6 to whatever I got for my AB, and so I end up getting this guy. Again, pi is kind of weird when you leave it like this. It's kind of like a like term. You can't combine it unless there's other pi's involved. Okay. Is pizza a pie, guys? I want to know that. Find that out for me, because I was just thinking about that. Is a pizza technically a pie, or is a pie technically a pizza? I don't know. Okay. Find that out for me, please. Area. The area of this entire sector, again, we're taking the area of the whole thing. So the area we're finding is, we're using this equation. Again, just plug in your radius, plug in your angle, and you're going to get 12 pi centimeters squared. Okay? Now, for the actual purple region, to find this area, okay, this is not a known shape. It's a very irregular shape. But we do have some things we do know. So if I want that segmented purple area, that's going to be equal to the area of sector AOB, so the whole area, what we just found. And I can actually subtract off this triangular area, and whatever's left over, that's going to be my shaded regions area. So let's go ahead and do that. We know the area of sector AOB already. That part's done. So now we just need the area of the triangle AOB. Well, we need to use that area equation that we got from law of sines and cosines. The 1/2 AB sine C. So we just need our 2 side lengths right here of our triangle, and then whatever the angle is in the middle. And it all actually kind of works out. So we plug everything in, and we end up getting 9 square root of 3 centimeters squared. And so to get my area of my segment, I need to do 12 pi minus 9 square root of 3. This is where you might want to use a calculator just to get that more exact answer. And so we end up getting 22.1 centimeters squared for the area of our shaded region. Okay. Now for part 2. Part 2 actually wanted us to find the length of chord AB. It wanted us to find this length right here. So how do we do that? Well, this is where we can use the law of cosines now. What we do have, we have an opposite side length to this angle, right? So remember what I was saying is, if you have an angle right here, the corresponding side is always opposite to that angle. And that's actually the side that we want to find, right? So what I do is, using the law of cosines, I'm going to find that opposite side length. I'm going to call it A. And so A squared is going to equal my B squared plus C squared sides, which are my radius, my radii, minus 2 times b times c times cosine of that angle 2 pi over 3. So I throw all that stuff in there. Yeah, throw it all on there. And we end up getting 108. And so I take the square root of both sides, and I get square root of 108, which is 6 square root of 3 centimeters. Okay? And that is the length of that chord using the law of cosines. How did I know to use the law of cosines? Again, law of cosines is really good when you have two sides, an angle in between, and then you want to find another side. That's really the only thought process I used. We went over it in our notes last time, and that's kind of when I told you to use law of cosines. So that was just kind of my dead giveaway. Let's see one more example. Let's see something that's a lot more geometrically demanding, let's say that, okay? Here's example 2. Example 2 is weird, okay? It says the diagram shows the cross-section of 3 pencils, each of radius 3.5 millimeters, held together by a stretched elastic band. We need to find the shaded region in here, and then in turn we have to find the stretched length of this outside band. Okay? What I would want you to do, I encourage you to pause the video and try to see if you can figure out a way to get the shaded area, because it's not as obvious as you might think. Alright, if you didn't pause the video, we're going to go over it anyway, okay? Well, I have a radius that's coming out of this, a radius of 3.5. Now, what I can do is, I can also include a radius here, my radius here, and I think you can kind of see what I'm doing. I'm making a triangle, but I'm not just making any kind of triangle. What is true about all these side lengths? Well, this side length of this triangle that I'm getting, it's 2r. It's 2 times the radius, which makes it a length of 7. Okay, so I'm going to call this just 3.5 for right now, so we have it. But all the side lengths are the same. Now, remember what we were talking about, depending on how large your angle is, that'll determine how large your opposite side is. Well, if all the side lengths are the same, that also implies all of our angles in here are also the same. Really what we have here, guys, is an equilateral triangle. So all of the angles in here, they all have to be the same, so they all have to add up to 180, meaning they are all 60 degrees, okay? Our angle is going to be 60 degrees in there. And what did I just do? Not only did I construct some kind of triangle, but I've constructed arcs too. I've constructed an arc right here, I've constructed an arc right here, and an arc right here. And it turns out if I want the shaded area in there, I want the area of this triangle, and then I'm going to subtract off each of these 3 sectors of my triangle. If I do that, I'm left over with the shaded region. Whenever you guys are looking for shaded areas and it's a weird old shape, try to figure out what you can find the area of first, like a bigger piece, and then what you can subtract off. They're always going to be nicer geometric shapes that we can make out of stuff to give us more irregular areas, okay? Easier said than done, I know. An area of a triangle, in this case, again, we use our area of our triangle equation because it can be used for any triangle, right? So I do 1/2 AB sine C. I know that sine C is, well, C is going to be the 60 degrees, but as a radian measurement, that'll be pi over 3 rads. And so I plug my 3.5 sides in there, okay? And what I end up getting is I end up getting 21.22 millimeters squared. So that's my area of my triangle. Well, now I want my area of my sector, of my sectors, but all the sectors are going to be the same. So if I find the area of one, I multiply it by 3. So to find the area of the sector, again, I use that sector equation, and so it's 1/2 times r squared times theta, plug in my r, plug in my theta. I get 6.41 millimeters squared. I'm going to go ahead and multiply that by 3 so I get all the area sectors. I get 19.24. And then get the shaded area. I take the area of the triangle minus my sector areas, and I get 1.98 millimeters squared, which makes sense. That's a pretty small area size, and if we look at our diagram, looks pretty darn small. Okay. Part 2. Part 2 is weird. I went ahead and I started doing a little bit more with this triangle. Okay. So part 2, it wants us to find the stretch length of this outer band right here. Again, not so straightforward, but if we think about the triangle that we made earlier, well, this triangle, it has a length of 2r. Well, if I think about it, what I can do is I can get really creative with my geometry. I can go ahead and I can make that this part of this band right here, just this part, is going to be a length of 2r, okay? And likewise, it's going to be 2r here and here as well. So that leaves us with these little arc parts. Well, luckily, we have a nice arc length equation to help us out, okay? And so, now the question becomes, well, okay, what's my angle going to be for r theta? Is it going to be 60 degrees, Mr. Knight? Well, no, not exactly, right? So 60 degrees was corresponding to like these sectors in here, right? These sectors in here. But now we're talking about a sector, or really a part of a sector that's like out here, okay? That's the shaded area that we want. That's kind of the angle that we're considering right here. Well, what I did was too, if you notice, I made like little rectangles here, kind of show that, hey, just this part is a length of 2r. Well, if I'm making rectangles, that means this part's 90 degrees, this part's 90 degrees. So we have a 360 degree circle. We have 60 degrees devoted to in here. We have 90 here, 90 here. So what's left over? Turns out it's only 120 degrees. And that is going to be the angle that we're considering for our arc length right here. As a radian measurement, it is 2 pi divided by 3. And so now we can take all this stuff and put it into kind of like a little perimeter equation, right? So the perimeter of the band is going to be 3 times, because we have 3 of these, 3 times 2r, and then it's also going to be 3 times r times theta, you know, the arc length out here. And if I add those up, I get the perimeter. I throw a bunch of stuff into an equation, kabam, and I end up getting 43 millimeters is the perimeter of this band on the outside, okay? These problems are hard. I'm just going to be straight up. But you have all the tools at your disposal that you're going to need. I would recommend definitely working with someone or asking for help, of course, or even just like looking stuff up online. I understand that not everything can be done in the classroom, so if you want to utilize online resources, I'm fine with that. That's actually a great part of learning. So don't hesitate to reach out for help if you need help on these. This is Mr. Knight signing off. Use those tools to your advantage, guys.